And an example of the research we did, which was recently featured in Wired, describes a new breakthrough in natural language processing, which people are calling the ImageNet moment, which is basically we broke a new state-of-the-art result in text classification, which OpenAI then built on top of our paper to do with more compute and more data and some different tasks to take it even further. And this is an example of something that we've done in the last 6 months in conjunction actually with my colleague Sebastian Ruder. An example of something that's being built in the FastAI library, and you're going to learn how to use this brand new model in 3 lessons time. And you're actually going to get this exact result from this exact paper yourself. Another example, one of our alums, Hamel Hussain, who you'll come across on the forum plenty because he's a great guy, very active, built a new system for natural language semantic code search. You can find it on GitHub, where you can actually type in English sentences and find snippets of code that do the thing you ask for. And again, that's being built with the FastAI library using the techniques you'll be learning in the next 7 weeks.
In production.
In production, yeah. Well, it's. I think at this stage it's part of their experiments platform, so it's kind of pre-production, I guess. And so the best place to learn about these things and get involved in these things is on the forums, where as well as categories for each part of the course, there's also a general category for deep learning where people talk about research papers, applications, so on and so forth. So even though today we're kind of going to focus on a small number of lines of code to do a particular thing, which is image classification, and we're not learning much math or theory or whatever, over these 7 weeks, and then part 2, another 7 weeks, we're going to go deeper and deeper and deeper. And so where can that take you? I want to give you some examples. That there is Sarah Hooker. She did our first course a couple of years ago. Her background was economics. Didn't have a background in coding, math, computer science. I think she started learning to code 2 years before she took our course. She helped develop something she started a nonprofit called Delta Analytics. They helped build this amazing system where they attached old mobile phones to trees in the Kenyan rainforests and used it to listen for chainsaw noises, and then they used deep learning to figure out when there was a chainsaw being used, and then they had a system set up to alert rangers to go out and stop illegal deforestation in the rainforests. So that was something that she was doing while she was in the course as part of her kind of class projects. What's she doing now? She is now a Google Brain researcher, which I guess is one of the top, if not the top place to do deep learning. She's just been publishing some papers. Now she is going to Africa to set up Google Brain's first deep learning AI research center in Africa. Now I'll say, she worked her ass off. She really, really invested in this course, not just doing all of the assignments, but also going out and reading Ian Goodfellow's book and doing lots of other things. But it really shows where somebody who has no computer science or math background at all can be now one of the world's top deep learning researchers and doing very valuable work. Another example from our most recent course, Christine Payne. She is now at OpenAI, and you can find her post and actually listen to her music samples she actually built something to do automatically create chamber music compositions that you can play and you can listen to online. And so, again, it's her background, math and computer science. Actually, that's her there, classical pianist. Now, I will say she's not your average classical pianist. She's a classical pianist who also has a master's in medical research from Stanford and studied neuroscience and was a high-performance computing expert at D.E. Shaw and was valedictorian at Princeton. Anyway, she, very annoying person, good at everything she does. But, I think it's really cool to see how a kind of a domain expert, in this case the domain of playing piano, can go through the FastAI course and come out the other end at, I guess OpenAI would be, of the 3 top research institutes, Google Brain and OpenAI would be 2 of them, probably along with DeepMind. And interestingly, actually, one of our other students, or I should say alumni of the course, recently interviewed her for a blog post series he's doing on top AI researchers. And she said one of the most important pieces of advice she got was from me. And she said the piece of advice was, pick one project, do it really well, make it fantastic. Okay, so that was the piece of advice she found the most useful. And we're going to be talking a lot about you doing projects and making them fantastic during this course. Having said that, I don't really want you to go to AI or Google Brain. What I really want you to do is go back to your workplace or your passion project and apply these skills there, right? Like, let me give you an example. MIT released a deep learning course, and they highlighted in their announcement for this deep learning course this medical imaging example. And one of our students, Alex, who is a radiologist, said, you guys just showed a model overfitting. I can tell because I'm a radiologist, and this is not what this would look like on a chest film. This is what it should look like, and this, as a deep learning practitioner, this is how I know that this is what happened in your model. So Alex is combining his knowledge of radiology and his knowledge of deep learning to assess MIT's model from just 2 images very accurately, right? And so this is actually what I want most of you to be doing, is to take your domain expertise and combine it with the deep learning practical aspects that you'll learn in this course and bring them together like Alex is doing here. And so a lot of radiologists have actually gone through this course now and have built journal clubs and American Council of Radiology practice groups. There's a Data Science Institute at the ACR now and so forth. And Alex is one of the people who's providing kind of a lot of leadership in this area. I would love you to do the same kind of thing that Alex is doing, which is to really bring deep learning leadership into your industry, into your social impact project, whatever it is that you're trying to do. So another great example was Melissa Fabros, who was a English literature PhD. I think she studied like gendered language in English literature or something. And actually, Rachel in a previous job taught her to code, I think. And then she came into the Fast AI course, and she helped Kiva, a micro-lending social impact organization, to build a system that can recognize faces. Why is that necessary? Well, we're going to be talking a lot about this. But because most AI researchers are white men, most computer vision software can only recognize white male faces effectively. In fact, I think it was IBM's system is like 99.8% accurate on common white face men versus 60% accurate, 65% accurate on dark-skinned women. So it's like, what is that, like 30 or 40 times worse for black women versus white men. And this is really important because for Kiva, black women are, perhaps the most common user base for their micro-lending platform. So Melissa, after taking our course, and again, working her ass off and being super intense in her study and her work, won this $1 million AI challenge for her work for Kiva. Karthik did our course and realized that the thing he wanted to do wasn't at his company, it was something else, which is to help blind people to understand the world around them, so he started a new startup. You can find it now, it's called Envision. You can download the app, you can point your phone at things, and it will tell you what it sees. And I actually talked to a blind lady about these kinds of apps the other day, and she confirmed to me this is a super useful thing for visually disabled users. And it's the level that you can get to with the content that you're going to get over these 7 weeks and with this software can get you right to the cutting edge in areas you might find surprising. For example, I helped a team of some of our students and some collaborators on actually breaking the world record for training. Remember I mentioned the ImageNet dataset? Lots of people want to train on the ImageNet dataset. We smashed the world record for how quickly you can train it. We use standard AWS cloud infrastructure, cost of $40 of compute to train this model using, again, FastAI library, the techniques that we learn in this course. So it can really take you a long way. So don't be kind of put off by this, what might seem pretty simple at first. We're going to get deeper and deeper. You can also use it for other kinds of passion project. So Helena Sarin, actually, you should definitely check out her Twitter account, Flagalista. This art is basically a new style of art that she's developed, which combines her painting and drawing with generative adversarial models to create these extraordinary results. And so I think this is super cool. I mean, she's not a professional artist. She is a professional software developer, but she just keeps on producing these beautiful results. And when she started, her art had not really been shown anywhere or discussed anywhere. Now there's recently been some quite high-profile articles describing how she is creating a new form of art. Again, this has come out of the FastAI course that she developed these skills. Or equally important, Brad Kensler, who figured out how to make a picture of Kanye out of pictures of Patrick Stewart's head. Also something you will learn to do if you wish to. This particular type of what's called style transfer was a really interesting tweak that allowed him to do some things that hadn't quite been done before. And this particular picture helped him to get a job as a deep learning specialist at AWS. So there you go. Another interesting example, another alumni actually worked at Splunk as a software engineer, and he designed an algorithm after like lesson 3, which basically turned out at Splunk to be fantastically good at identifying fraud. We'll talk more about it shortly. If you've seen Silicon Valley, the HBO series, the Hot Dog Not Hot Dog app, that's actually a real app you can download, and it was actually built by Tim Onglade as a FastAI student project. So there's a lot of cool stuff that you can do. Yes, it was Emmy nominated. So I think we only have one Emmy nominated FastAI alumni at this stage. So please help change that. All right. The other thing, is the forum threads can kind of turn into these really cool things. So Francisco, who's actually here in the audience, he's a really boring McKinsey consultant like me, right? So Francisco and I both have this shameful past that we were McKinsey consultants, but we left and we're okay now. And he started this thread saying like, oh, this stuff we've just been learning about building NLP in different languages, let's try and do lots of different languages. And he started this thing called the Language Model Zoo. And out of that, there's now been an academic competition was won in Polish that led to an academic paper, Thai state-of-the-art, German state-of-the-art. Basically, students have been coming up with new state-of-the-art results across lots of different languages, and this all is entirely being done by students working together through the forum. So please, get on the forum, but don't be intimidated. Because remember, a lot of the, everybody you see on the forum, the vast majority post all the damn time, right? They've been doing this a lot, and they do it a lot of the time. And so at first it can feel intimidating, because it can feel like you're the only new person there. But you're not, right? All of you people in the audience, everybody who's watching, everybody who's listening, you're all new people, right? And so when you just get out there and say like, okay, all you people getting new state-of-the-art results in German language modeling, I can't start my server. I try to click the notebook and I get an error. What do? People will help you. Okay? Just make sure you provide all the information. This is the, I'm using Paperspace. This was the particular instance I tried to use. Here's a screenshot of my error. People will help you. Okay? Or if you've got something to add. So if people are talking about crop yield analysis and you're a farmer and you think, oh, I've got something to add, so please mention it. Even if you're not sure it's exactly relevant, it's fine. Just get involved. And because remember, everybody else on the forum started out also intimidated. Right? We all start out not knowing things, and so just get out there and try it. Okay, so let's get back and do some more coding. Yes, Rachel, do we have some questions?
Yeah, there's there's just a question from earlier about why you're using ResNet as opposed to Inception.
So the question is about this architecture. So there are lots of architectures to choose from, and it would be fair to say there isn't one best one. But if you look at things like the Stanford Dornbench benchmark for ImageNet classification, you'll see in first place and second place and third place and fourth place is FastAI, Jeremy Howard and FastAI, Jeremy Howard, FastAI, Yaroslav's from the Department of Defense Innovation Team, Google, ResNet, 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 ResNet. ResNet's good enough, okay? So it's fine. There are other architectures. The main reason you might want a different architecture is if you want to do edge computing, so if you want to create a model that's going to sit on somebody's mobile phone. Having said that, even there, most of the time I reckon the best way to get a model onto somebody's mobile phone is to run it on your server and then have your mobile phone app talk to it. It really makes life a lot easier and you get a lot more flexibility. But if you really do need to run something on a low-powered device, then there are some special architectures for that. So the particular question was about Inception. That's another architecture which tends to be pretty memory intensive ResNet. So Inception tends to be pretty memory intensive, but it's okay. It's also like, it's not terribly resilient. One of the things we try to show you is like stuff which just tends to always work, even if you don't quite tune everything perfectly. So ResNet tends to work pretty well across a wide range of different kind of details around choices that you might make. So I think it's pretty good. So we've got this trained model, and so what's actually happened, as we'll learn, is it's basically creating a set of weights. If you've ever done anything like linear regression or logistic regression, you'll be familiar with coefficients. We basically found some coefficients and parameters that work pretty well. And it took us 1 minute and 56 seconds. So if we want to start doing some more playing around and come back later, we probably should save those weights so we can save that 1 minute and 56 seconds. So you can just go learn.save and give it a name. Okay. It's going to put it in a model subdirectory in the same place the data came from. So if you save different models for different data bunches from different data sets, they'll all be kept separate, so don't worry about it. All right, so we talked about how the most important things are how to learn what goes into your model, what comes out. We've seen one way of seeing what goes in. Now let's see what comes out. Okay, so this is the other thing you need to get really good at. So to see what comes out, we can use this class called classification interpretation. And we're going to use this factory method from learner. So we pass in a learn object. So remember, a learn object knows two things. What's your data? And what is your model? It's now not just an architecture, but it's actually a trained model inside there. And that's all the information we need to interpret that model. So we just pass in the learner, and we now have a classification interpretation object. And so one of the things we can do, and perhaps the most useful things to do, is called plot top losses. So we're going to be learning a lot about this idea of loss functions shortly. But in short, a loss function is something that tells you how good was your prediction. And so specifically, that means if you predicted one class of cat with great confidence, you said, I am very, very sure that this is a Burman, but actually you were wrong, then that's going to have a high loss because you were very confident about the wrong answer. Okay, so that's what it basically means to have a high loss. So by plotting the top losses, we're going to find out what were the things that we were the most wrong on, or the most confident about but we got wrong. So you can see here, it prints out 3 things. German shorthead, or 4 things. Beagle, 7.04, 0.92. Well, what do they mean? Perhaps we should look at the documentation. So we've already seen help, right? And help just prints out a quick little summary. But if you want to really see how to do something, use doc. And doc tells you the same information as help, but it has this very important thing, which is show in docs. So when you click on show in docs, it pops up the documentation for that method or class or function or whatever. It starts out by showing us the same information about what are the parameters it takes, along with the doc string, but then tells you more information. So in this case, amongst other things, it tells me the title of each shows the prediction, the actual, the loss, and the probability that was predicted. So for example, and you can see there's actually some code you can run. So the documentation always has working code. And so in this case, it was trying things with handwritten digits. And so the first one, it was predicted to be a 7. It was actually a 3. The loss is 5.44. And the probability of the actual class was 0.07. Okay, so we did not have a high probability associated with the actual class. I can see why it thought this was a 7, but nonetheless it was wrong. So this is the documentation, okay? And so this is your friend when you're trying to figure out how to use these things. The other thing I'll mention is if you're a somewhat experienced Python programmer, you'll find the source code of FastAI really easy to read. We try to write everything in just a small number of, much less than half a screen of code, generally 4 or 5 lines of code. If you click source, you can jump straight to the source code, right? So here is the plot top losses. And this is also a great way to find out how to use the FastAI library, because every line of code here, nearly every line of code is calling stuff from the FastAI library. Okay? So don't be afraid to look at the source code. I've got another really cool trick about the documentation that you're going to see a little bit later. Okay, so that's how we can look at these top losses, and these are perhaps the most important image classification interpretation tool that we have, because it lets us see what are we getting wrong. And quite often, like in this case, if you're a dog and cat expert, you'll realize that the things it's getting wrong are breeds that are actually very difficult to tell apart, and you'd be able to look at these and say, oh, I can see why it got this one wrong. Okay? So this is a really useful tool. Another useful tool, kind of, is to use something called a confusion matrix, which basically shows you, for every actual type of dog or cat, how many times was it predicted to be that dog or cat. But unfortunately, in this case, because it's so accurate, this diagonal basically says, oh, it's pretty much right all the time. And you can see there's some slightly darker ones, like a 5 here, but it's really hard to read exactly what that combination is. So what I suggest you use is, instead of, if you've got lots of classes, don't use a confusion matrix. But this is my favorite named function in FastAI. I'm very proud of this. You can call most confused. And most confused will simply grab out of the confusion matrix the particular combinations of predicted and actual that it got wrong the most often. So in this case, the Staffordshire Bull Terrier was what it should have predicted, and instead it predicted an American Pit Bull Terrier, and so forth. It should have predicted a Siamese and actually predicted Burman. That happened 4 times. This particular combination happened 6 times. So this is, again, a very useful thing, because you can look and you can say, like, with my domain expertise, does it make sense that that would be something that was confused about? So these are some of the kinds of tools you can use to look at the output. Let's make our model better. So how do we make the model better? We can make it better using fine-tuning. So far we fitted 4 epochs, and it ran pretty quickly. And the reason it ran pretty quickly is that there was a little trick we used. These deep learning models, these convolutional networks, they have many layers. We'll learn a lot about exactly what layers are, but for now just know it goes through computation. What we did was we added a few extra layers to the end, and we only trained those. We basically left most of the model exactly as it was. So that's really fast. And if we're trying to build a model of something that's similar to the original pre-trained model, so in this case similar to the ImageNet data, that works pretty well. But what we really want to do is actually go back and train the whole model. So this is why we pretty much always use this 2-stage process. So by default, when we call fit or fit one cycle on a conv learner, it'll just fine-tune these few extra layers added to the end, and it'll run very fast. It'll basically never overfit. But to really get it good, you have to call unfreeze. And unfreeze is the thing that says, please train the whole model. And then I can call fit one cycle again, and, the error got much worse. Okay, why? In order to understand why, we're actually going to have to learn more about exactly what's going on behind the scenes. So let's start out by trying to get an intuitive understanding of what's going on behind the scenes. And again, we're going to do it by looking at pictures. We're going to start with this picture. These pictures come from a fantastic paper by Matt Zeiler, who nowadays is CEO of Clarify, which is a very successful computer vision startup, and his supervisor of his PhD, Rob Fergus. And they created a paper showing how you can visualize the layers of a convolutional neural network. So a convolutional neural network will learn mathematically about what the layers are shortly, but the basic idea is that your red, green, and blue pixel values, that are numbers from 0 to 255, go into a simple computation, the first layer, and something comes out of that, and then the result of that goes into a second layer, and the result of that goes into a third layer, and so forth. And there can be up to 1,000 layers of a neural network. ResNet 34 has 34 layers, ResNet 50 has 50 layers. But let's look at layer 1. There's this very simple computation. It's a convolution. If you know what they are, we'll learn more about them shortly. What comes out of this first layer? Well, we can actually visualize the specific coefficients, the specific parameters, by drawing them as a picture. There's actually a few dozen of them in the first layer, so we won't draw all of them, but let's just look at 9 at random. So here are 9 examples of the actual coefficients from the first layer. And so these operate on groups of pixels that are next to each other. And so this first one basically finds groups of pixels that have a little diagonal line in this direction. This one finds diagonal lines in the other direction. This finds gradients that go from yellow to blue in this direction. This one finds gradients that go from pink to green in this direction, and so forth. And so they're very, very simple little filters. That's layer 1 of a ImageNet pre-trained convolutional neural net. Layer 2 takes the results of those filters and does a second layer of computation. And it allows it to create, so here are 9 examples of kind of a way of visualizing this, one of the second layer features. And you can see it's basically learned to create something that looks for corners, top left corners. And this one has learned to find things that find right-hand curves. And this one has learned to find things that find little circles. Right? So you can see how layer 2, like this is the easiest way to see it. In layer 1, we have things that can find just one line. In layer 2, we can find things that have 2 lines joined up, or one line repeated. If you then look over here, these 9 show you 9 examples of actual bits of actual photos that activated this filter a lot. Right? So in other words, this little bit of function, math function here, was good at finding these kind of window corners and stuff like that. This little circly one was very good at finding bits of photos that had circles in. Okay, so this is the kind of stuff you've got to get a really good intuitive understanding for. It's like the start of my neural net's going to find simple, very simple gradients and lines. The second layer can find very simple shapes. The third layer can find combinations of those. So now we can find repeating patterns of two-dimensional objects, or we can find kind of things that lines that join together, or we can find, well, what are these things? Well, let's find out. What is this? Let's go and have a look at some bits of picture that activated this one highly. Oh, mainly they're bits of text, although sometimes windows. So it seems to be able to find kind of like repeated horizontal patterns. And this one here seems to be able to find kind of edges of fluffy or flowery things. This one here is kind of finding geometric patterns. Right? So layer 3 was able to take all the stuff from layer 2 and combine them together. Layer 4 can take all the stuff from layer 3 and combine them together. By layer 4, we've got something that can find dog faces. And let's see what else we've got here. Yeah, various kinds of, oh, here we are, bird legs. So you kind of get the idea. And so by layer 5, we've got something that can find the eyeballs of birds and lizards, or faces of particular breeds of dogs, and so forth. So you can see how by the time you get to layer 34, you can find specific dog breeds and cat breeds, right? This is kind of how it works. So when we first fine-tuned that pre-trained model, we kept all of these layers that you've seen so far, and we just trained a few more layers on top of all of those sophisticated features that are already being created. Right? And so now we're fine-tuning, we're going back and saying, let's change all of these. We'll start with them where they are, right? But let's see if we can make them better. Now, it seems very unlikely that we can make these layer 1 features better. Like, it's very unlikely that the definition of a diagonal line is going to be different when we look at dog and cat breeds versus the ImageNet data that this is originally trained on. So we don't really want to change layer 1 very much, if at all. Whereas the last layers, this thing of like types of dog face, seems very likely that we do want to change that. Right? So you kind of want this intuition, this understanding that the different layers of a neural network represents different levels of kind of semantic complexity. So this is why our attempt to fine-tune this model didn't work, is because we actually, by default, it trains all the layers at the same speed, right? Which is to say it'll update those like things representing diagonal lines and gradients just as much as it tries to update the things that represent the exact specifics of what an eyeball looks like. So we have to change that. Okay? And so to change it, we first of all need to go back to where we were before. Okay? We just broke this model, right? It's much worse than it started out. So if we just go load, this brings back the model that we saved earlier. Remember we saved it as stage 1? Okay? So let's go ahead and load that back up. So that's now, our model's back to where it was before we killed it. And let's run Learning Rate Finder. We'll learn about what that is next week. But for now, just know this is the thing that figures out what is the fastest I can train this neural network at without making it zip off the rails and get blown apart. Okay, so we can call learn.lrfind, and then we can go learn.recorder.plot, and that will plot the result of our LR finder. And what this basically shows you is there's this key parameter that we're going to learn all about called the learning rate. And the learning rate basically says how quickly am I updating the parameters in my model. And you can see that what happens is, as this bottom one here shows me what happens as I increase the learning rate, and this one here shows what's the result, what's the loss. And so you can see once the learning rate gets past 10 to the negative 4, my loss gets worse, right? So it actually so happens, in fact I can check this, if I press Shift Tab here, my learning rate defaults to 0.003. So my default learning rate is about here. So you can see why our loss got worse, right? Because we're trying to fine-tune things now, we can't use such a high learning rate. So based on the learning rate finder, I tried to pick something, well before it started getting worse. So I decided to pick 1e neg 6. So I decided I'm going to train at that rate. But there's no point training all the layers at that rate, because we know that the later layers worked just fine before when we were training much more quickly. Again, it was the default, which was, to remind us, 0.003. So what we can actually do is we can pass a range of learning rates to learn.fit. And we do it like this. You use this keyword in Python, you may have come across it before, it's called slice, and that can take a start value and a stop value. And basically what this says is train the very first layers at a learning rate of 1e neg 6, and the very last layers at a rate of 1e neg 4, and then kind of distribute all the other layers across that, between those two values equally. So we're going to see that in a lot more detail, right? But basically, for now, this is kind of a good rule of thumb, is to say after you unfreeze, so this is the thing that's going to train the whole thing, pass a max learning rate parameter, pass it a slice, make the second part of that slice about 10 times smaller than your first stage. So our first stage defaulted to about 1e neg 3, so let's use about 1e neg 4. And then this one should be a value from your learning rate finder, which is well before things started getting worse. And you can see things are starting to get worse maybe about here. So I pick something that's at least 10 times smaller than that. So if I do that, then I get 0.05788. So I don't quite remember what we got before. Yeah, a bit better, right? So we've gone down from a 6.1% to a 5.7%. So that's about a 10 percentage point relative improvement with another 58 seconds of training. So I would perhaps say for most people, most of the time, these two stages are enough to get pretty much a world-class model. You won't win a Kaggle competition, particularly because now a lot of Fast AI alumni are competing on Kaggle, and this is the first thing that they do. But, in practice, you'll get something that's, about as good in practice as the vast majority of practitioners can do. We can improve it by using more layers, and we'll do this next week by basically doing a ResNet 50 instead of a ResNet 34. You can try running this during the week if you want to. You'll see it's exactly the same as before, but I'm using ResNet 50 instead of ResNet 34. What you'll find is, it's very likely if you try to do this, you will get an error. And the error will be, your GPU has run out of memory. And the reason for that is that ResNet 50 is bigger than ResNet 34. And therefore it has more parameters, and therefore it uses more of your graphics card's memory, which is totally separate to your normal computer RAM. This is GPU RAM. If you're using the kind of default Salamander, AWS, and so forth suggestion, then you'll be having 16 gig of GPU memory. The card I use most of the time has 11 gig of GPU memory. The cheaper ones have 8 gig of GPU memory. And that's kind of the main range you tend to get. If yours has less than 8 gig of GPU memory, it's going to be frustrating for you. Anyway, so you'll be somewhere around there. And it's very likely that when you try to run this, you'll get an out-of-memory error. And that's because it's just trying to do too many parameter updates for the amount of RAM you have. And that's easily fixed. This image data bunch constructor has a parameter at the end, batch size, BS for batch size. And this basically says, how many images do you train at one time? If you run out of memory, just make it smaller. Okay, so this worked for me on an 11 gig card. It probably won't work for you if you've got an 8 gig card. If you do, just make that 32. It's fine to use a smaller batch size. It might take a little bit longer. That's all. Okay, if you've got a bigger, like a 16 gig, you might be able to get away with 64. Okay, so that's just one number you'll need to try during the week. And again, we feed it for a while, and we get down to a 4.4% error rate. So this is pretty extraordinary. I was pretty surprised because, when we first did in the first course just cats versus dogs, we were kind of getting somewhere around a 3% error for something where you've got a 50% chance of being right, and the two things look totally different. So the fact that we can get a 4.4% error for such a fine-grained thing, it's quite extraordinary. In this case, I unfroze it and fitted a little bit more, went from 4.4 to 4.35, it's a tiny improvement. Basically, ResNet 50 is already a pretty good model. It's interesting because, again, you can call most confused here, and you can see the kinds of things that it's getting wrong. And I actually, depending on when you run it, you're going to get slightly different numbers, but you'll get roughly the same kinds of things. So quite often I find that Ragdoll and Berman are things that it gets confused, and I actually have never heard of either of those things. So I actually looked them up on the internet, and I found a page on the cat site called "Is This a Berman or a Ragdoll?" And there is a long thread of cat experts arguing intensely about which it is. So I feel fine that my computer had problems. I found something similar. I think it was this Pit Bull versus Staffordshire Bull Terrier. Apparently the main difference is the particular kennel club guidelines as to how they are assessed. But some people think that one of them might have a slightly redder nose. So this is the kind of stuff where actually even if you're not a domain expert, it helps you become one, right? Because I now know more about which kinds of pet breeds are hard to identify than I used to. So model interpretation works both ways. So what I want you to do this week is to run this notebook, make sure you can get through it. But then what I really want you to do is to get your own image data set. And actually, Francisco, who I mentioned earlier, he started the language model thread, and he's now helping to TA the course. He's actually putting together a guide that will show you how to download data from Google Images, so you can create your own data set to play with. But before I do, I want to...
There's also one more question.
Okay, I'll come back to that in a moment. Before I do, I want to show you how to create labels in lots of different ways, because your data set, wherever you get it from, won't necessarily be that kind of regex-based approach. It could be in lots of different formats. So to show you how to do this, I'm going to use the MNIST sample. MNIST is pictures of hand-drawn numbers. Just because I want to show you different ways of creating these data sets. The MNIST sample basically looks like this. So I can go path.ls, okay? And you can see it's got a training set and a validation set already. So basically the people that put together this data set have already decided what they want you to use as a validation set. Okay, so if we go path/train.ls, you'll see there's a folder called 3 and a folder called 7. Right? Now this is really, really common way to give people labels. It's basically to say, oh, everything that's a 3, I'll put in a folder called 3. Everything that's a 7, I'll put in a folder called 7. Right? This is often called an ImageNet style data set, because this is how ImageNet is distributed. So if you have something in this format where the labels are just whatever the folder's called, you can say from folder. Okay? And that will create an image data bunch for you. And as you can see, 3, 7, it's created the labels just by using the folder names. Another possibility, and as you can see, we can train that, get 99.55% accuracy, blah, blah, blah. Another possibility, and for this MNIST sample I've got both, it might come with a CSV file that would look something like this. For each file name, what's its label? Now in this case, the labels aren't 3 or 7, they're 0 or 1, which is basically, is it a 7 or not? Right? So that's another possibility. So if this is how your labels are, you can use from CSV. And if it's called labels.csv, you don't even have to pass in a file name. If it's called anything else, then you can pass in the CSV labels file name. Okay, so that's how you can use a CSV. Again, there it is. This is now, is it a 7 or not? Another possibility, and then you can call data.classes to see what it found. Another possibility is, as we've seen, is you've got paths that look like this. And so in this case, this is the same thing. These are the folders. Right? I could actually grab the label by using a regular expression. And so here's the regular expression. So we've already seen that approach. And again, you can see data.classes has found it. So what if it's something that's in the file name or the path, but it's not just a regular expression, it's more complex? You can create an arbitrary function that extracts a label from the file name or path. And in that case, you would say from name and function. Another possibility is that you did something even more flexible than that, and so you're going to write some code to create an array of labels. And so in that case, you can just pass in from lists. So here I've created an array of labels. Here are my labels. Here's from lists, okay? And then I just pass in that array. So you can see there's lots of different ways of creating labels. So during the week, try this out. Now you might be wondering, how would you know to do all these things? Like, where am I going to find this kind of information, right? How do you possibly know to do all this stuff? So I'll show you something incredibly cool. Let's grab this function. And do you remember, to get documentation, we type doc. And here's the documentation for the function, and I can click show in docs. And it pops up the documentation. So here's the thing, every single line of code I just showed you, I took it this morning and I copied and pasted it from the documentation. So you can see here the exact code that I just used. So the documentation for FastAI doesn't just tell you what to do, but step to step how to do it. And here is perhaps the coolest bit. If you go to FastAI, FastAI_docs, and click on docs source, it turns out that all of our documentation is actually just Jupyter notebooks. So in this case, I was looking at vision.data. So here is the vision.data notebook. You can download this repo, you can git clone it, and if you run it, you can actually run every single line of the documentation yourself. Okay, so all of our docs is also code. And so like this is the kind of the ultimate example to me of experimenting, right? Is that you can now experiment, and you'll see in GitHub it doesn't quite render properly because GitHub doesn't quite know how to render notebooks properly. But if you git clone this and open it up in Jupyter, you can see it. And so now, anything that you read about in the documentation, nearly everything in the documentation has actual working examples in it with actual data sets that are already sitting in there in the repo for you. And so you can actually try every single function in your browser. Try seeing what goes in and try seeing what comes out.
There's a question, will the library use multi-GPU in parallel by default?
The library will use multiple CPUs by default, but just one GPU by default. We probably won't be looking at multi-GPU until part 2. It's easy to do, and you'll find it on the forum, but most people won't be needing to use that now.
And the second question is whether the library can use 3D data, such as MRI or CAT scan.
Yes, it can, and there is actually a forum thread about that already. Although that's not as developed as 2D yet, but maybe by the time the MOOC is out, it will be. So before I wrap up, I'll just show you an example of the kind of interesting stuff that you can do by doing this kind of exercise. Remember earlier I mentioned that one of our alums who works at Splunk, which is a NASDAQ-listed, big, successful company, created this new anti-fraud software. This is actually how he created it as part of a FastAI Part 1 class project. He took the telemetry of users who had Splunk Analytics installed and watched their mouse movements, and he created pictures of the mouse movements. He converted speed into color and right and left clicks into splodges. He then took the exact code that we saw with an earlier version of the software and trained a CNN in exactly the way we saw, and used that to train his fraud model. So he basically took something which is not obviously a picture, and he turned it into a picture, and got these fantastically good results for a piece of fraud analysis software. So it pays to think creatively. So if you're wanting to study sounds, a lot of people that study sounds do it by actually creating a spectrogram image and then sticking that into a ConvNet. So there's a lot of cool stuff you can do with this. So during the week, get your GPU going, try and use your first notebook, make sure that you can use lesson 1 and work through it, and then see if you can repeat the process on your own data set. Get on the forum and tell us any little success you had. It's like, oh, I spent 3 days trying to get my GPU running and I finally did. Any constraints that you hit, try it for an hour or 2, but if you get stuck, please ask. And if you're able to successfully build a model with a new data set, let us know. And I will see you next week.